In this video, I want to look at another example of patching up a U substitution through the idea of inverse substitutions. I want to look at the following example from the textbook. Now, this is actually a fairly hard example. I would like you to stop the video, read through the example, and then restart the video to see what I say about it. So hopefully you've done that. What I want to do is I want to start by looking at the very first sentence of this. The author starts out by choosing a U without saying anything about why he's chosen this U. It's important to realize that he's chosen that U because the U is the denominator of his fraction that is making up the integrand up here. And then he says that du is equal to this. And that's kind of a strange looking expression. And taking the derivative of the square root of 2x plus 3 is not something that many calculus students can do immediately in their head. So the first thing that I want to do is I want to put that derivative taking back into the example. If u is equal to the square root of 2x plus 3, then what I know is this: du dx will be 1/2 times 2x plus 3 to the negative 1/2 times the derivative of 2x plus 3, which is a 2. And that means the 2's are going to cancel out. When I convert this derivative into differential notation, we get du is equal to 2x plus 3 to the negative 1/2 times a dx. Well, something to the negative 1/2 is 1 over that something. So we get this particular expression, and that's why du turns out to be dx over the square root. Now, once you have that, the rest of the substitution becomes much easier. But taking that derivative, finding the du here, is hard. So I want to look at an alternate solution where finding the du is much, much easier. So let's get started. Here's another copy of the problem. Now what I'm going to do is I'm going to notice that we do have a composition here. We have a square root of a 2x minus 3. Now I already know that if I take the whole derivative of the square root of 2x minus 3, I don't quite have exactly what I'm wanting to have, and I've got this leftover x. So instead, what I'm going to do is I'm simply going to make u equal to something easier, just the stuff underneath the square root sign. And when I do that, the du simply becomes 2 dx. And so if I put a 2 over 2, that 2 and that dx form together to make the du. And so at this point, my integral now looks like 1/2 the integral of, well, gee, I still have that stupid x inside the integral, but the rest of this is going to be the square root of u du, because this u and the dx went into that du. Now, if I look at this, u is equal to 2x minus 3. It is easy to solve that equation for x. We have u minus 3 is equal to 2x. We have u minus 3 divided by 2 is equal to x. And I am going to put this in for the x up here inside this integral sign. So this is going to go into the integral. And when I do that, the integral is going to become 1/2 times the integral of u minus 3 over 2 over that square root of u times du. Now, I know that many students have trouble dealing with algebraic expressions like this, and so I want to do the algebra very carefully, one step at a time. And the first thing that I'm going to do is I'm going to do something that is going to make handling the fractions easier. I'm going to turn the square root of u into a square root of u divided by 1. Anything divided by 1 is, of course, itself. But now that I have a fraction over a fraction, I can do the standard invert and multiply. And when I do, I have 1/2 times the integral of u minus 3 over 2 times 1 over the square root of u times the du. And if you use this trick, it'll help you deal with fractional messes like what we had before and get everything correct. Now I'm going to pull this 2 outside my integral sign, and when I do that, we're going to get 1/4 times the definite integral of u minus 3 over, and now u to the 1/2, the square root of u can be written as u to the 1/2, and I need to make my fraction clearer. That's u to the 1/2. And the reason I want to do this is I'm going to break this fraction up at this plus sign, this minus sign in the top, because that is a legitimate piece of arithmetic. So I can rewrite this integral as 1/4 times the integral of u divided by u to the 1/2 minus 3 over u to the 1/2, and then I've got the du. And when I look at exponent rules, this will then become something that is relatively straightforward for integrating. I can rewrite this as 1/4 times the integral of, well, u divided by u to the 1/2 is just u to the 1/2. And another way of writing 3 divided by u to the 1/2 is to say that I've got minus 3 times u to the minus 1/2. And at this point, I want to notice that both of these are easy to integrate. The 1/4 is going to multiply everything. So I'm going to have 1/4 times u to the 3/2 divided by 3/2 minus 3 times u to the 1/2, divide by that new exponent of 1/2, and add a constant. Now all I have to do is back substitute and clean up the fractions. I think I will do the back substitution after I clean up the fractions. What we are looking at here is 1/4 times 2/3 times u to the 3/2 minus 6 times u to the 1/2 plus a constant. And when I multiply the 1/4 through, I'm going to get 1/6 times u to the 3/2, because we will have 2/12, and 2/12 will cancel to 1/6. And when I multiply 1/4 by 6, I'm going to get 2. Well, let's actually do the scratch work over here so I don't mess up the arithmetic. The scratch work is 6/4, and that's going to be 3/2. So I will have 3/2 times u to the 1/2 plus that constant. For my final answer, all I have to do is go back and find out what the heck u was, and we simply scroll all the way back to the top, and we find out that u is equal to 2x minus 3. And so my final answer is 1/6 times 2x minus 3 to the 3/2 minus 3/2 times 2x minus 3 to the 1/2 plus a constant. And then if we wanted to get the answer in the back of the book, the answer that the authors had, it's enough to realize that this term here is just a square root of 2x minus 3. In other words, the authors have written the answer in this particular fashion. But it's the same thing, and we can confirm that by simply going backwards and checking their answer. And you will notice that there is exactly what we just got done computing. Now, my point is, you can do this problem in either way. If this particular substitution makes more sense to you than the author's does, then that is fine. And so you need to choose which way makes more sense. There's sometimes more than one way of working a math problem.